Welcome everyone. Let's talk about first derivative test. Suppose that f is continuous at a critical point x0. So this means derivative at this point is equal to 0. Our first case, if f derivative is positive in an open interval immediately to the left of x0 and negative in an open interval immediately to the right of x0, then f has a local max at x0. What do we mean? If I know a critical point, I can make the sign table. Let's say this is our sign table at the point x0. From the definition, our left is going to be positive and our right is going to be negative. This is negative infinity and this is infinity. I know on this interval the function is increasing and on this interval it is decreasing. Therefore, there's a local max at x0. Think of a function that behaves like this. For example, a function like this, first increasing, then decreasing. Clearly, at the top, I have a local maximum. Our second case, again, f derivative, and the critical point is x0, negative infinity, and infinity. This time, on this interval, I will be negative, and on this interval, I will be positive, therefore, decreasing, and then increasing. Try to visualize a graph in your head. Anything that behaves like this, there is a local minimum here. If it does not change the sign, of course, at the critical point x0, let's say positive, positive, it will keep increasing, therefore, you will not have a local max. And if it's negative, negative, so decreasing, again, what can I show it like? Like this maybe. Again, no local minimum. Let's talk what we learned about first derivative until now. So, first derivative. First, with the help of first derivative, we can find critical points. Second, with the help of first derivative, we can find increasing, decreasing intervals. And lastly, we can find local max mins. These are the applications of our first derivative. We have second derivative applications as well. We will talk about that in the next video. For now, let's try to apply what we learned about first derivative. Problem: apply the first derivative test to the function. First, critical points. Second, increasing, decreasing. And lastly, local max, min. All comes from the first derivative. Let's start. Differentiating the given function. Of course, we all know how to differentiate these functions at this point. X squared minus 8x plus 15 is equal to 0. Let's find the critical points. X minus 5 multiplied by x minus 3 is equal to, yep, it is. This is equal to 0. Roots are 5 and 3. We finished the first part. For the other two steps, we need the sign table. You can draw the sign table any way you want. I'm used to showing it this way, so I show it this way. This is the notation I'm used to. We have two critical points, 3 and 5. Let's pick a number from right of the 5, 6 for example. 6 squared, 36 minus 8, 48 plus 15, 51 minus 3, so positive. Let's pick a number between 3 and 5, for example 4. 16 plus 4, 16 plus 1, 4, 31 minus 48, clearly negative. Let's pick something less than 3, maybe 2. 2 squared 4, 19 minus 16 positive. Increasing, decreasing, and increasing. We did the second step. Lastly, local max and min. Local maximum is going to be at, we don't need to have one, but in this case we have, because increasing, then decreasing. Think of it again. If you don't know the definition, you can always imagine a graph. I know after increasing, then decreasing, I have a local max, which is at 3, f of 3. You need to plug this point in the function because not on the derivative. Do not make that mistake because this point belongs to the function. Local minimum. Let's think how can we have a local minimum. First we will decrease, then increase, so we will have a min. Do we have that? Yes, we do. We have that at 5, 5, f of 5. Let me see the function. You can evaluate f of 3 and f of 5 by yourself. It's algebra, so I will leave that to you. Find and classify all relative extrema for the given function. Relative extrema means local min or local max. Both are relative extremas. So again, first differentiating the function is equal to, I have a composite function, 3x minus 2 squared is equal to 0. Now I look at this function, I have only 2 as a root. Making the sign table is my second step. I can never draw a straight line. Maybe like this. 2 is here, infinity, negative, infinity. Let's pick a number, 3. 3 minus 2, 1 squared 1, so positive. I think a number less than 2, but no matter what, this is going to be positive, so we do not have a local extrema because the function is always increasing. Increasing. Find and classify all relative extrema for the function. Again, we will have to follow the same steps, but we have to be careful at a specific point in this function, which is 2. Even though x is equal to 2 is not a critical point, we have to be careful because on the sign table, I need to see this function, the point I mean, because this point could be a point where the function changes its behaving. Let's see, differentiating this function, 2x multiplied by, of course, we will differentiate it according to the division, minus x squared minus 3 over x minus 2 squared. This is equal to 2x squared, 2x squared minus 4x, 2x squared minus 4x minus x squared minus plus 3 over x minus 2 squared, which is also equal to x squared minus 4x plus 3 over x minus 2 squared. Now, I want this to be equal to 0, so x squared, instead of x squared minus 4x plus 3, I will write x minus 1 by x minus 3 over x minus 2 squared. This is equal to 0. So the points I will have on my sign table are 1, 3, and 2. Because as you can see, it makes the denominator 0. If a point makes the denominator 0 when you differentiate the function like we did, it should also be on the sign table of the first derivative. 1, 2, 3. 1, 2, 3. Picking the points will not be fun, I guess, but let's see. Let's pick 4, right side of 3. Positive, clearly. Let's pick a number between 2 and 3, 2.5 maybe. Denominator is positive no matter what. Oh yeah, and we need to show 2 with 2 lines to know that it's not a critical point. I forgot that. 2 is not a critical point. Between 2 and 3, 2.5 for example, this part is positive, this is negative, so this part is negative. Let's make sure, yes it is. Between 1 and 2, for example, 1.5. Denominator is no matter what positive. This is positive, this is negative, so this is negative as well. And something less than 1, for example, 0, which is positive. Increasing, decreasing, decreasing, and increasing. We know the critical points. Let's write everything. Critical points. X is equal to 1 and x is equal to 3. X is equal to 2 is not a critical point. Increasing, decreasing intervals. We showed it with arrows. Lastly, local max and min. What do we have? First increasing and decreasing, so at 1 and f of 1, I have a local max. Do I have another local max? No. If this was, well, if this was increasing, then we would have 1 at 2, but we did not have the sign change, so therefore we don't. Local minimum is going to be at 3 and f of 3, of course. We will not put anything for 2 because the sign does not change. It keeps decreasing on this interval from 1 to 3.